Chapter 6 of Ralph 124C41 Plus. The following day was set aside for a visit to the accelerated plant growing farms. It had been given for hundreds of years that certain plants, such as mushrooms, can be fully developed in a few days. Plants and animals grown under glass and the temperature within kept at a high point will grow at a great speed and be ready for the market long before those grown in the open. But only recently, as Ralph explains to Alice, has it been possible to do this on a large scale. To be sure, certain vegetables like asparagus, lettuce, peas, etc. have been produced in hothouses for hundreds of years, but these, after all, are rather luxuries and cannot be classed as essentials. When about the year 2600, the population of the planet has increased tremendously and famines due to lack of such essentials as bread and potatoes have broken out in many parts of the world, it is found vitally necessary to produce such necessities on a larger scale and with unfailing regularity. These farms become known under the term of accelerated plant growing farms and are located in every part of the world. The first and now obsolete European and African farms are built along the lines of the old-fashioned hothouses. The European farms are simply horizontal steel latticed roof with ordinary glass panes permitting the sunlight to penetrate to the soil beneath. While covering huge acreages, they are not heated artificially, using only the sun's rays to accelerate plant growth. As compared with nature's single crop of wheat or corn, two can be made to grow in the same season by means of these super hothouses. Similar farms are used in America until Ralph undertakes their study and approaches the subject from a scientific angle. One of his first efforts is to obtain greater heat for these hothouses. One of the hothouses is about 3 miles long and the same width. Ralph takes the existing hothouses, which are simply oblong steel and glass boxes, and builds a second hothouse box covering each of them, thus created a double-walled, air-locked hothouse. The second glass-paneled wall was about 2 feet inside the outer one. This left dead air locked between the walls, and as air is a poor heat conductor, the heat in the hothouse is retained longer, particularly during a cold night. Ralph and Alice leave early in the morning, winging their way in the Aeroflyer toward northern New York, where there are many accelerated plant-growing farms. When the farms come into view, the entire country below appears to be dotted with the glass-covered roofs of the plant, reflecting the sunlight and affording an unusual sight. Alice marvels at their number, for while she has seen some of these farms in Europe, she has never seen so many grouped together. Within a few minutes, they land near one of the giant hothouses. The manager leads them inside the farm, labeled number D1569. D1569 is exclusively a wheat-growing farm where Mother Nature used to grow 1 crop of wheat a year. Ralph's latest accelerator makes it possible to grow 4, and sometimes 5 crops a year. In the old-fashioned European farms, such as Alice knows, there are only 2 crops that could be grown. How is it possible, she asks, that you can obtain 3 more crops a year than we do in Europe? In the first place, says Ralph, we know that the more heat you supply to plant growth, the quicker it will grow. Cold and chilly winds retard plant growth. Electricity and certain chemicals increase the ratio of growth, a fact that has been known for many centuries. It is, however, a scientific application of this knowledge that makes it possible to raise 5 crops a year. The European farms use only the heat of the sun to stimulate plant growth, but during the night, when the temperature drops, growth is practically nil. Notice that the top and sides of our hothouses have 2 walls. In other words, one hothouse is built within another. The air locked between the 2 hothouses is an excellent heat insulator, and even though the sun is low at 4 o'clock, the temperature is practically unchanged in the hothouse at 8 or 9 o'clock in the evening. Even in the winter, when the sun sets at about 4 o'clock and it is cold, we are able to store up enough heat during the day to keep a high temperature as late as 7 or 8 o'clock. If we do nothing between the hours of 8 in the evening and 8 in the morning, the temperature will continue to fall to a point where no plant growth will be possible. Here in America, we have had to have a greater production to supply our huge population. It is a pure case of necessity, so we have to employ artificial heating during the night. If we start sinking a shaft into the earth, the heat increases rapidly, but go down more quickly in some parts of the world than others. On an average, the temperature rises about 1 degree Fahrenheit every 100 feet of depth. We have found it economic, therefore, to use the Earth's own heat to heat our farms. By means of high-speed drills, we can cut a 3-foot shaft 3,000 feet deep in the earth in less than a month. We go down until we strike a temperature around 100-120 degrees Fahrenheit, then we lower steel tanks into the cavity and run pipes up to the surface. tanks are filled with water, and 2 larger pipes run from each tank into the circulating system of pipes around the lower walls throughout the length and breadth of the farms. The shafts are then closed at the top, and we have a circulating system that is both cheap and efficient. The hot water continually rises into the pipes and circulates. As it cools, it flows down again into the tanks, where it is reheated and rises again. Thus, the temperature of our farms is uniform all the year round, and plant growth is as rapid during the night as during the day. Heat alone, however, is not sufficient. We should still get only a normal growth. We wanted 5 crops a year. I put my research forces to work studying fertilizers. While the old nitrogen fertilizers were excellent, they were not suitable for high-pressure, high-speed growing methods. We evolved chemicals which were both cheap and easy to apply. We found that small quantities of termidon, when mixed with water and sprayed over the field by overhead sprayers, which you will see running along the ceiling, will accelerate the growth of crops enormously. This liquid termidon is sprayed over the entire length and breadth of the field before planting time so that the soil becomes well soaked. The termidon immediately turns the soil into a rich dark strata, the best soil for potatoes, wheat, or corn. No other fertilizer needs to be used, the termidon applied after every growth, giving the soil all the vitality necessary. They were now in the field when suddenly Alice asks, "What is the particular tingling in the soles of my feet I feel as we walk along? You are using some electrical vibrations, I suppose." "You guessed correctly," Ralph replies. "With all our artifice, the speed of the plant growth has not been accelerated sufficiently. I therefore insulated the inside hothouse from the ground. The inside hothouse rests upon glass blocks and is electrified by high-frequency currents. The entire area is sprayed day and night with a high-frequency current, in the use of which we found was the real secret of driving plant growth ahead at enormous speed." The theory, of course, is nothing new, having been known for centuries. What is new, however, is the way it is done. It makes all the difference in the world if the current density is too high or too low, if it is direct or alternating current, and many other details. I found the quickest way to accelerate plant growth by electricity was to send the current from the growing plant toward the ceiling, and the current must be direct, pulsating, but not alternating. Ralph asks for a discharge pole from one of the attendants. It is a metal pole about 7.5 feet high. In the middle, it has a long glass handle which Ralph grasps. He then sets the pole vertically so that its top is about 6 inches from the glass ceiling. A roar of fine sparks leaps from the steel frame of the ceiling to the top of the pole. "See," Ralph says, "there is a current we use in accelerating the growth of our plants." Removing the pole, Ralph continues, "The electrical current density per square foot is not very high, and the wheat does not get a very great amount of electricity during the 24 hours. The continuance of the force applied is what counts." After luncheon, during which they ate some of the bread made from the wheat grown on the premises, they go to an adjoining farm, also a wheat farm, where harvesting is full progress. Machinery suspended from overhead tracks cuts the wheat rapidly with circular scythes. All the wheat being of the same height, the machine cuts the wheat almost directly below the heads, dropping them onto a conveyor which carries the real harvest to the central distribution point. Another machine immediately follows the cutter, grasping the stalks that are still standing, unerringly pulling out the straw hulks, root and all. Thus the roots are entirely removed and the soil loosened, obviating plowing. Within a few hours following cutting, the last stem is out. The field is then sprayed with the liquid termidon from overhead. Within another 3 hours, sowing begins, also from overhead pipes. Going to an adjoining plant, they see a bare field with almost black soil ready to be sowed. The attendant, at Ralph's request, pulls a switch, and immediately Alice witnesses a seed rain from the overhead pipes. "The seed," Ralph explains, "is supplied to these tubes by means of compressed air. The tubes are perforated, and when air pressure is applied, the seeds flow through the pipes and they are ejected evenly, just so many seeds to a given area. Closing the openings of the pipes automatically as the seeding proceeds means only a given quantity of seed will fall upon any given square foot of soil. This makes for a scientific planting, and we raise just the exact quantity of wheat we want." Alice watches the seed rain spellbound. Like a wall of rain, it slowly recedes into the distance until finally it disappears. "How long does it take to sow this field?" she asks. "From 2 to 3 hours, depending upon the size of the field. This particular field is about 8 miles long and 3 miles wide. The process should be completed within about 3.5 hours. "And when will this crop be ready for harvest?" Alice wants to know. "In about 70 days from now, the wheat will be ready to cut." Alice walks along thoughtfully and then inquires whether the great cost of such an undertaking will not make the growing of the foodstuffs prohibited. "Quite the contrary," Ralph replies. "We are now growing wheat, corn, potatoes, and many other foodstuffs for a much lower price than our ancestors did 500 or 600 years ago. You see, it is the installation of the hothouses and machinery that is costly, but these glass and steel buildings will last for centuries with proper care. Frames are made of non-rusting steel, which needs no painting. The glass lasts for hundreds of years. The labor we use in planting and harvesting is a mere fraction of what was used in olden times. Thus, for sowing and harvesting this plant 8 miles by 3, we only need 20 people. There is a very much smaller number than we used to use in the old-fashioned farms. We waste nothing. We have no poor crops, and we get 3 or 4 times as much as our ancestors did. They step up to a glass case containing samples of wheat grown for hundreds of years, showing that the head of wheat grown in the year 1900 is about 3 inches long, while the present year's crop shows a length of more than 6 inches, or twice as much flour content per stalk. Ralph also points out to Alice that the modern wheat stalk is much bigger in circumference than the ancient one, which he explains is attributable to the great weight of the modern wheat. The old stalks could not possibly have supported such a great weight of grain, so it is necessary to cultivate bigger stalks. Ralph goes on, "As I said before, we waste nothing here. The harvested hulks go to the paper mill a few miles away and are converted into a first-class paper. A few decades ago, an entirely new paper process was invented. Where straw was used once for making so-called straw board or cardboard, the finest commercial papers are now being made from the straw grown right here. We no longer annihilate our forests to make paper pulp. Since the invention of the straw paper process, chopping trees for paper purposes has been forbidden, and all the paper in this country is now made exclusively of straw chemically treated." A potato farm is seen the same afternoon. The processes in this and other vegetable growing plants being under somewhat different conditions than the wheat farm. It is dark when Alice and Ralph return to the wheat farm, number 1D1569, and find that the manager of the plant has prepared an elaborate supper for the two, informing Alice that everything set before her has been grown the same day. The whole wheat bread has been harvested that morning, the grains had been artificially heated by heat, flour has been made, and the bread has been baked. He says somewhat proudly that this is probably a record. The entire meal consists of vegetables all grown in plants in the vicinity. There are peas, asparagus, potatoes, lettuce, apples, and more delicacies. For dessert, the manager brings in on a great silver tray a number of new cross foods, which as yet had not been seen in the open market. There is the cross between an apple and a pear, which has all the good qualities of the apple and all the good qualities of the pear. There is also the delightful combination of the plum and the cherry, a cantaloupe with a faint taste of orange, and cherries as big as good-sized plums. Tea is served from tea leaves grown in one of the farms and harvested the same day. The manager also shows Alice cigarettes and sets before Ralph a box of cigars made from tobacco planted and harvested that day. The leaves have been aged rapidly by dry heat in a partial vacuum. Both thank the manager for the novel treat. After dining, they walk into the wheat-growing farm. It is now dark outside, but in the hothouse the wheat for miles and miles seems to be aglow in a light purple haze. A faint, half-crackling, half-swishing sound is heard, and the points of the wheat seem to be almost luminous. "This is the night appearance of the electricity you felt this afternoon," says Ralph. "During the day you do not see the faint discharge, but in the dark it becomes luminous. One pole of the high-frequency generator is connected with the soil, and the other with the steel framework of the hothouse. Without the electric current, we would not be able to grow more than 2 or at the utmost 3 crops a year. It is also necessary to vary the strength of the current during the day. With full sunshine and maximum heat, we do not need as much current as we use during the night. Several hundred years ago, when using somewhat similar methods that had not as yet been perfected, it is necessary to use artificial light during the night, as plants need light for growth. We found, however, that the electric current with the soft light which you see glowing now is sufficient for the purpose, and the plant does not require any other light." Alice stands for many minutes silently watching the beautiful sight of the glowing purple field, listening to the faint crackling discharge of the electric current as it leaps from the points of the wheat into the air. They finally leave and fly back to New York. The next day, Ralph takes Alice to one of the city's synthetic food laboratories. While flying towards it, Ralph explains that while the farms which they had looked over yesterday were for the purpose of raising real foodstuffs, there are many commodities that could not be so raised, such as sugar, milk, and many others, which are now made synthetically. As chemists have known for many hundreds of years, sugar is nothing but a simple carbohydrate, whereas milk is composed of an emulsified mixture of casein, lactic acid, butter, water, and minor constituents. As the population increases, it is neither possible nor profitable to obtain these foods by natural means, and it is found necessary to resort to the chemist. They alight at one of these chemical laboratories which manufactures sugar, milk, cooking fat, butter, and cheese. There is really not much to see except large boulder-like chemical retorts, large white enameled vats, and a lot of pumps and electric motors. The manager explains that sugar is made out of sawdust and acids. The sawdust, he explains, is digested in a huge white enamel steel vat by means of certain acids. After the digesting process is completed, other chemicals are added, the ensuing syrup then being run through retorts and finally emerges as a stream of sugar. The manager hands Alice a piece of clear, transparent sugar, as well as several specimens of crystallized sugar, which she eats delightedly, explaining laughingly that it is the best sawdust she had ever eaten. The next visited the synthetic milk section, where hundreds of thousands of gallons of milk are produced every day. This being a recent discovery, the manager explains it in detail. Milk, he says, has been known since the dawn of humanity. But only when man has become somewhat civilized does he learn how to obtain milk from animals such as the goat and the cow. It takes thousands of years to domesticate these animals, and it is not known at what period man first began to milk these domestic animals for his own supply of milk. Men of an inquisitive nature must have asked themselves the question for thousands of years: why grow grass? Let the cow eat the grass, digest it, and finally turn it into milk. Why not eliminate the cow entirely? The thought, while elementary, has no actual basis or foundation for centuries, because the chemical processes of the intermediate stages between the grass and the final milk are too complicated and are not at all well understood. Only during the last few years has the problem been solved satisfactorily. Now we grow fresh grass, which we put into these large retorts, where the grass is digested just the same as if it were in the stomach of a cow. By the addition of salts and chemicals, we imitate the digestive process, and by eliminating solids and liquids, we finally get a milk that is not only better than the original cow or goat, but has many qualities not possessed by cow's milk. Try this glass of artificial milk, he says to Alice, handing her a glass of rather unappetizing-looking liquid of a slightly pale green color, not too clean-looking, and somewhat thick. The manager asks Alice to close her eyes and take a good drink. She does so and exclaims in surprise that it tastes exactly like rich, creamy milk. The manager then explains that synthetic milk is free from bacteria, which gives milk its white color. Moreover, the fat content is much higher than cow's milk, and there being a greater percentage of sugar present, the milk tastes sweeter. Certain added salts give it a distinguishing taste. From this milk, he further explains, any sort of fat can be extracted, and the usual array of milk products, such as butter, all sorts of cheeses, etc., can be made much better than from cow's milk, which never ran uniform. After inspecting the laboratory, Ralph and Alice sample a number of products, all of which taste excellent, better, if anything, than the natural products. The manager adds, you will find our synthetic products are far easier to digest and are more wholesome than the natural product. The reason is that we have eliminated all of the disease-carrying microbes and bacteria, retaining only the beneficial ones, which we can control very easily in our plants, more than the cow or goat can do. End of chapter 6.